You did this in your IGs. Now remember, all of you see the board?
Yes.
Okay. Only one person said yes.
Yes.
Yes, this is Safa. Okay. Now there are classifying reactions is many ways, but the most common way for which we will require them is there are two types of reactions, that is reversible and irreversible in terms of the direction of the reaction. What is the meaning of reversible? Anyone? Yes, please.
Reaction can the product can form the reactants again.
Yes. So reversible reaction actually takes place in both the direction. Takes place in both directions. Now, when you say both direction, what are the both directions? The forward and backward. So in our equilibrium chapter, in our chapter for equilibrium, we are focusing only on reversible reactions. How do you represent this? Irreversible only in one direction. Only in one direction. How do you represent a reversible reaction, Mariam?
With the arrows going front and back, half arrows.
Good. Either you can show it this way, or you can show half arrows. Both means the same thing. So you can show it either ways, and that represents a reversible reaction. Now there are a few conditions important for a reaction to be at equilibrium. So equilibrium is a condition. Now in your exam, they can use the word equilibrium. They can use the word chemical equilibrium, or they can use the word dynamic equilibrium. It all means the same. So first thing, let's understand the definition for this. Can anyone give me the definition for this? Yes, please. Anyone? Tasneem, you are there? Tasneem, you are there? Yes, Tasneem Khalid.
Yes.
Why everyone has switched off your mic? Yes, Tasneem. Do you know the definition?
No.
Okay, Safa?
Definition of dynamic equilibrium?
Anything. In the exam they can say equilibrium, they can say chemical equilibrium, they can say dynamic, anything. Is the same definition.
Is it when it's like constant?
No. In a reversible reaction. So the important thing is reversible reaction. In a reversible reaction, when the rate of forward reaction is equal to rate of backward reaction. The reaction is said to be at equilibrium. Is this thing clear? So there are two conditions over here. One condition is that it has to be a reversible reaction. The second condition is the rate of forward has to be equal to the rate of backward. If these conditions are met, then you will say that the reaction has reached equilibrium. Now, why do you call it as dynamic? Anyone? Why do you call it as dynamic?
Is it because it needs to happen in a closed environment?
No, that's a different thing. Dynamic means something which is changing. So here you are already talking about rate. Rate means the reaction is taking place. So because of this term, you know that it is dynamic. Dynamic means the reaction is still going on. Is this thing clear? Is this thing clear?
Yes.
Yes.
So
Yes.
since the like if you leave your laptop at one place, tomorrow you come over there, it is still there. So that is at equilibrium, but that is a static equilibrium because there was no changes taking place. In chemistry, we don't talk about a static equilibrium. We talk about dynamic because the reaction is still taking place. How do we know the reaction is still taking place? Because there is a forward and the backward reaction taking place. Now, for the reaction to attain equilibrium, it has to be done in closed container. Now, usually it's better to write this, but closed container is only required when you have gases involved. You have gases which are involved over there. Like for example, if you are carrying out a reaction between nitrogen and hydrogen in an open vessel, what will happen? Nitrogen and hydrogen will combine together, ammonia will escape out. So there is no reaction there is no ammonia for the backward reaction to take place. Is this thing clear? Or,
Yeah.
Yes.
or let us say you have a beaker of water. You have a beaker of water and you leave it for a few days. What will you observe?
It's gonna
It's evaporated.
So what will you, again, that is your wrong observation.
Less volume of water.
Yes, very good. So the level will decrease. The level may come down. Clear? That is because it is only in one direction. The H2O liquid is changing into H2O gas. But suppose you cover it. Now what happens?
The volume will not change because when it's evaporate, it's condensed again.
Yes, so very good. So what happens is the water vapor, it goes out over here, then the amount is more, so they condense back. So there are two reactions taking place, this going over here as well coming back. Is this thing clear?
Yes.
So a point will come where the level remains same. Level does not change. And this is the point where the equilibrium is achieved. Did everyone understand?
Yes.
Okay.
Yes.
So there are, let's,
Teacher, I
yes,
have a question. You know the definition that you gave in the beginning? That's for
yes.
what, equilibrium or dynamic?
I told you it is the same thing. You
Okay.
call it as equilibrium, you call it as chemical equilibrium, you call it as dynamic, everything is the same.
Okay.
Okay, now the next thing, let's try to understand this graphically. That's the more important thing. Graphically, how to show the equilibrium. So we know this from the rate of the reaction chapter, that the rate depends on the amount. The rate depends on the amount. So let us say this is the rate, this is the progress of reaction. This is progress of reaction. Now for forward reaction, I should start from here or I should start from here. From the top or from the bottom? Forward reaction. Yes, please.
From the top?
Yes, because initially the amount of the reactants would be more, so the rate will be fast. As the reactants convert into products, what happens is its amount keeps on decreasing. Keeps on decreasing. So this is, you are showing rate of forward. Any problem?
The amount of product decreases.
Reactant decreases.
Oh yeah, sorry, reactant, yeah.
Because you have the reactants converting into products. So initially
Yes.
this would be maximum and this would be 0. So this will keep on decreasing with time. And now as the reaction proceeds, the products will keep on increasing. So initially the product is 0. As the reaction proceeds, the rate of the backward reaction will keep on increasing like this. They will meet at a point. This is rate of backward. After this, they go together. Now at this point, the rate of forward is equal to rate of backward. So this is a time where the equilibrium is achieved. Is this thing clear?
Yes.
Like you come from one door to the school, your friend comes from another door to the school, and then you meet together and go in the corridor together. This is the way. So this is a way to show that the rate of forward is equal to the rate of backward. Any questions for this?
No.
Okay. What happens to the concentration when the equilibrium is reached? Concentration or amount?
Does it stay the same?
Remains the same.
Very good. So there are two different things over here. Rates are equal, but the concentration or the amount remains the same. Like for example, let us say I have a reaction H2 plus I2 changes into twice HI. Now let us say the total amount of this is 10 moles. Initially, the total amount of this is 0 moles. This is at time 0. Now as the reaction proceeds, the forward reaction is more. I just showed you on the graph. It keeps on decreasing till it reaches, let us say 3 moles. This keeps on increasing till it reaches 7 moles. At this point, the rate of forward becomes equal to rate of backward. So what will happen? The speed at which this converts into this will be the same speed at which this will convert into this. Is this thing clear?
Yes.
So what is going to happen with time? With time, this will remain 3 moles and this will remain 7 moles. Did everyone get this?
Sorry, can you repeat that part?
Okay, I'm saying at any given time,
Yes.
that depends on the reaction condition, suddenly the rate of forward becomes equal to rate of backward. Now at this point, what will happen is if 1 mole of reactants per minute are converted into products, so in the same time, 1 mole of the product will also convert into the reactant because the rate is the same.
Yes.
So the amount of the reactant is not going to change, amount of the product is not going to change, even though the reactants are converting into products and the products are converting into a reactant. Like you are on a treadmill,
Yeah.
you are walking, you do walk, but you do not cover any distance. You're getting the point? Because
Yes.
the treadmill, the belt goes back.
So because it's taking place at the same time, that's why
No,
it remains the
same rate. Same rate. The problem
Okay.
is this thing, when the equilibrium is reached, then the conversion of the reactant to the products and the products to the reactant is at the same speed.
Okay.
So therefore, finally or overall, there is no change. Like if I give you 1 pen and you give me 1 pen, we still both have 1 pen.
Yes.
Same thing is happening over here. So that can be explained in terms of, again, graphical representation of rate. These graphs are important. Graphical representation of in terms of concentration. Now let us say this is the concentration of the reactants or the products, because we have to talk about both of them. So initially the amount of the concentration of the reactants would be more. It will keep on decreasing. Let us say it decreases to 3 moles and then it will go slowly like this. At infinity, it will meet somewhere. They explain you that point in maths. That is called as something asymptomatically, something like that. I don't remember that. So this is for your reactants. Now what will happen with the products? Initially the products are 0. Clear? Is this thing clear to all of us?
Yes.
And
Yes.
then it keeps on increasing till it becomes somewhere constant. Okay, let me draw this also as a constant to explain it, but in actually it will not be constant, it will be slightly parallel to that. So let's say this thing. So the point where they become constant, they do not change. That is the point where the equilibrium is reached. This is the point where the equilibrium is reached. So what is happening is the amount of the product remains constant. The amount of the reactants remain constant with time. Is this in clear?
Yes.
Is this
You
okay?
mean the concentration?
Yes, amount. The problem here is I'm using the concentration, but in
Yeah.
actual practice, I have explained you for the rate that you could measure the concentration, you could measure the amount, you can measure moles, anything.
Yeah. Okay.
Now this is one graph. The other manipulation of this graph is like here I'm considering that the equilibrium is reached when the amount of the reactant is less. There is also a possibility. There is also a possibility that the reactance decreases. This is the reactant, and this is a product. So here also they become constant. So you can see it's not important that the reactant amount has to be less. It can be more or less, anything. It is not important. What is important is that the amount of the reactant and the product remain constant. Is this in clear?
Yes. Yes.
So it is not important that it has to be product has to be more than reactant. Even the reactant can be more than product and still the equilibrium is achieved. Like when the teacher is teaching, sometimes the teacher says half the point you understand, and sometimes the teacher has to repeat 10 times, then you understand. So both the conditions are possible. Same thing is over here. So this is the way you represent the equilibrium in terms of concentration or equilibrium in terms of rate of reaction. The most important thing, they will ask you what is the features of equilibrium. Is usually 2 to 3 marks. Features means how will you know that the reaction is at equilibrium, or when the reaction is at equilibrium, what happens? Yes, please.
The rate of forward reaction equal to the rate of backward reaction.
Very good. Then that's very good.
Concentration is constant.
Yes, so see, this is very important. We are not saying concentration equal. We are saying concentration of reactants and products remain constant. They are not equal. They are constant. Then any other thing? Any other thing?
I don't know.
Does something to do with pressure?
So in all these things, you can, there's pressure, temperature, everything. You can say the state variables. What's the meaning of state variables? Remain constant. State variable means the properties that can change. Variable means properties that can change in a reaction. Properties that can change. So they will remain constant. Like, for example, what are the examples of the state variables? The temperature, the pressure, the color, the smell, all these things.
Could it be?
Yes.
Could it be also the state of the reactant or product, like solid, liquid, gas?
We can't say that. The reason is the reaction is still going on, so it will the reactants and the products are together. So you will not know the changes over there. But temperature you can
okay.
measure, pressure you can measure. You're getting the point? In a beaker,
Yeah.
in a beaker, the reactants and the products are together, so you cannot figure out that.
Yeah. Okay.
So this is the three main features of equilibrium. Now, why do
Can you
we
explain
state?
the second point? The
Sorry?
concentration. Can you explain the second point, the concentration one?
Concentration of the reactant or the product remain constant. This is what I have explained you over here.
Okay.
That once the equilibrium is achieved, what happens is the speed at which the reactants convert into products is the same speed as which the product converts into reactant. So what is happening is there is no change.
Okay.
Like I explained over here, this thing, this part.
Yeah.
There you got 3 moles and 7 moles, but then the rate became equal. Now the equilibrium was established. So because of this, the speed at which the reactants are converting into product is the same speed at which the products convert into reactants. So there's no change in the amount.
Okay.
Okay. Any questions till now?
No.
Okay. So the next thing is, why are we so interested in this chapter for equilibrium or this concept of equilibrium? Definitely one is the exam that we don't know now. What is the other thing? The problem is that reversible reactions are never completed. Why are they never completed? Anyone?
Because they're always going to be like going on product to reactant, reactant to
Yes,
product.
because, very good, because they reach equilibrium. So once they reach the equilibrium, what would happen is, once they reach the equilibrium, the concentration of reactant and product remain constant. So that means it is not going to end, because for ending, the amount of the reactant needs to be 0. So here what is going to happen? At any given point, the equilibrium will be reached, and then the reaction will, even though it is using the resources, it is not going to produce any more product. Is this thing clear?
Yes.
Now,
Yes.
so how does it affect us? It affects us because there are many industrial process. There are many industrial manufacturing process where reversible reactions are used, where reversible reactions are involved. So what happens is they are utilizing the resources, but the amount of the product is not increasing. For example, you have N2 plus 3H2. They put this in one container and then leave it. Before, what the industrialists used to do was they will put this in a container, and then they will leave it, thinking when the reaction will be complete, you will get 100% of this. But what happens? An equilibrium is established.
You'll get.
Yes, equilibrium will
It
be
will
established.
reach equilibrium.
Yes, very good. So once it reaches equilibrium, the amount of this and this remains constant. So there is no 100% yield of the product. Is this thing clear?
Yes.
So that is a wastage of labor, that's a wastage of electricity, and so on, so many things. So what we are going to study now is we are going to study about manipulation of equilibrium conditions. Equilibrium conditions. Why? Safa, why do we want to manipulate the equilibrium condition?
So that you can get more product.
Very good. So our aim is to get maximum product. So this is our aim. So we want to manipulate the equilibrium so that we can see how to which reaction condition would be the best to get the maximum product. Is this thing clear? This is
Yes.
explained. This is explained on the basis of Le Chatelier's principle. Before I explain you what it is, let's say you are standing over here. Someone comes and applies force over here. Tasneem, what will happen to you? What will you do? Tasneem, Khalid is there, I think.
Yeah.
Yes. What will happen?
Move.
What will you do? You are standing, someone comes and pushes you in the forward direction. What will you do?
Apply a resistant force in the opposite direction.
Opposite, same amount. So that you will apply the force in the opposite direction, same amount. Why? Because you want to stay in your equilibrium position. You don't want to fall off. Is this thing clear?
Yes.
Same thing happens with the reaction. Exactly the same thing happens with the reaction. We know that at equilibrium, the temperature, pressure, concentration, all these things remain constant. So if you increase any one of them, the reaction will try to decrease it. If you decrease it, the reaction will try to increase it. That's the basic concept of Le Chatelier principle. Whatever you will do, the reaction will try to do the opposite. Clear?
If you decrease what?
If you decrease any of the state variables,
Okay.
or increase, so basically you are manipulating. Let us say, for example, if you increase the temperature, what the reaction will do? The reaction will try to decrease it.
Okay.
If you decrease the pressure, what the reaction will do? It will try to increase it. If you increase the concentration, what the reaction will do? It will try to increase it. Yeah, if you increase, it will decrease. Yes. So it is trying to do the opposite. Clear?
Yeah.
Okay.
That is the main concept of the Le Chatelier. So according to Le Chatelier principle, what happens is, how will you define it? In a reversible reaction. So the important thing is the reaction needs to be reversible reaction at equilibrium. So we are talking about a condition when a reversible reaction is at equilibrium. Any change in temperature, pressure, concentration, what will happen? If any change in temperature, pressure, or concentration, what happens is the reaction prefers a direction to undo or nullify the effect of the change. The effect of the change. So what we are saying, the first important thing is that it has to be reversible, it has to be equilibrium. Now, if you change any temperature, pressure, or concentration, what will the reaction do? The reaction will prefer a direction. Which direction it will prefer? So that it can undo that effect. Undo means you are increasing. Like when you type it something wrong on your computer, there is an undo, a back arrow like this when you're typing. So what you do is you undo that effect. You're getting the point?
Yeah.
So whatever you will do, the reaction will try to do the opposite. This is what we have to learn now. If I increase the temperature, what the reaction will do? Means it prefers a direction. So which direction it can do? If I decrease the pressure, which direction the reaction will try to do? That's what we are going to
increase.
Yes. So, but how we will know which direction is increased? That's what we are going to. That's what we are going to learn. Which direction the temperature can be decreased? So I will take an example. The most common example, N2 plus 3H2 gives you ammonia, and I will use this as a reaction to explain all the conditions. But this can be applied for any reversible reaction. So let's say, first of all, I am explaining you effect of concentration. Usually we talk about the reactants, but it can be similarly applied to the products also. So we know the reaction is at equilibrium. So right now what I'm doing is I'm increasing the concentration of reactants. Now reactants could mean in your exam, they may just say nitrogen, they may just say hydrogen, or they may say reactant. It means the same thing. It means you are increasing the reactant. I'm explaining you the whole, I'm giving you the explanation. If the exam, they can ask you the explanation, then what you will see, what you will write. So increased concentration of reactant, what happens is the equilibrium is disturbed. Any problem with this?
No.
Why the equilibrium is disturbed?
No.
Why the equilibrium is disturbed?
Because you've changed the amount.
So why it is disturbed? Because
Because the concentration
It will do
changed.
the opposite.
yes, no. We are talking about why equilibrium is disturbed. Equilibrium is disturbed because at equilibrium the concentration has to remain constant. It has to remain constant and you have changed it. Did you understand? Did you get everyone this point? So
Yes.
at equilibrium, the concentration needs to be constant. But what you are doing is you are adding more of nitrogen or hydrogen. So the equilibrium gets disturbed. So what will the reaction do? Yes,
Is it because the concentration is changing when you're adding more?
Yes, increase means you have changed the concentration. And at equilibrium, it needs to be constant. So you have disturbed it. Like someone was sleeping, you wake him up. So you have disturbed him. So reaction prefers to, what it will do, it will try to decrease the concentration. First you will write down this.
Shift the part with lower concentration?
No. Reaction prefers to decrease the concentration. That means it is trying to oppose it. Why? So opposing means what you have done, you have increased. What the reaction is doing, decrease. Clear?
Yeah.
Now in this reaction, how can the reaction decrease the amount of the reactants? Remember, it has only two options, either the forward direction or the backward direction. How can it decrease the amount of the reactants?
By increasing the amount of product?
Very good. So that means very good. So the reaction will prefer, the reaction prefers the forward direction. Clear?
But teacher, if you're trying to get less reactant.
Yes, so the only way is the reactant gets converted into product, so the amount of the reactants will decrease.
Okay.
You're getting the point. If the reactants get converted into products, so what will happen to the reactants? The reactants will decrease.
Decrease. Yeah.
Yes, but in your exams, they don't want this forward direction. At A levels, even at IG, they want it in terms of left or right. So you should better use the word equilibrium position shifts to right. That means the forward direction is dominating, or the right direction is dominating. When it was at equilibrium, both were 50-50%. You can understand it this way. Both the rate of forward and the rate of backward were 50%. Now when you increase the concentration, what is happening? The forward has become 80% and the backward is now only 20%. Did you understand?
Yes.
This is what I'm trying to say, that the forward becomes dominating now. So the equilibrium position shifts to the right. And if it is shifting to the right, that means the forward direction is preferred. Then definitely what will happen is more of product. Now in this case, your product is ammonia formed. Always your explanation has to be in terms of products, never in terms of reactants. You can say more of this, or you can say the percentage yield of product is more. Is this clear?
Teacher, can you repeat that last point?
I'm saying our aim was in terms of products. Remember, that's what you said.
Yes.
Our main aim is to get the maximum amount of the product. So your explanation has to be in terms of whether your products are more or less.
Okay.
That is at the end you have to talk about this, whether the product is more or product is less. Clear?
Okay.
Okay. So this was when you increase the concentration of the reactant. Any questions, anyone? Any questions from anyone? No one says anything. So what should I? Do you hear me?
Yes.
Yes.
Okay, now, okay. So now same way, if you decrease the concentration of the reactant, the equilibrium will decrease. The reaction will prefer to increase the concentration. That means again it is opposing it. So the reaction will prefer the backward direction. And the equilibrium position shifts to the left. And in this case, what will happen is less of product obtained. Clear to us?
Yes. Sure, can you explain it again? I'm kind of confused.
See, if you are increasing the concentration of the reactants,
yeah,
what will happen? The first thing is your equilibrium is disturbed. We know that. Why? Because the concentration of the reactants should be constant and you are changing it. So what will the reaction do? The reaction will try to do the opposite. You have increased it, the reaction will try to decrease it. How it will decrease? By using the reactants. So in which direction the reactants will be used up? When it converts into products.
yeah.
So that's why it is preferring the forward, or you say the better word is equilibrium position shifts to the right.
So that way
So
more product is formed, so then it
definitely.
So,
Yes,
yeah.
correct. That's the main. Now the next thing is the effect of temperature.
Teacher?
Yes.
If the equilibrium is shifting to the right, does that mean it's shifting to the NH3 side, the product side?
Yes.
So, okay. So
That
when it
was
shifts
our
to
aim.
so whichever side it shifts to, that increases.
Correct.
Okay.
But our final conclusion should be based on the amount of the product, whether the product is more or less. Like for example, in this case also, over here I have said the reaction prefers the left direction. So yes. I'm not saying the reactants have increased. I'm still talking about the products only.
Okay, so you're just saying everything in terms of product.
Yes, because our aim was the amount of product.
Okay.
Our aim is how much of product is formed. Our aim is not the reactant. Clear?
Teacher?
Yes.
How do we know that it prefers to go forward or backward?
For which thing? For concentration?
Yes.
Okay, that's the simple thing. That's what I was explaining. If you are increase the reactants, if you increase reactants, then it is always to the right. If you decrease the reactants, that is what I was just explaining in detail, then it prefers the left. Right means forward and left means backward. Clear?
Yes.
So that is how you can remember that. So this is the way to remember what happens when you change the concentration. Now let's talk about the temperature. What is the effect of temperature over here? Now for temperature, we need to understand few things before. How will you know which direction? Okay, before the. Now we should know only the main point, that is if you increase the temperature, what will the reaction do? The reaction will try to decrease it, correct? Any problem with this? If you increase the temperature, the reaction should decrease it. Decrease means use up. Use means it will prefer the endothermic direction. Why endothermic direction? Because in endothermic direction, it will absorb the energy. And this is how it can lower the heat. Whatever temperature you have increased, the reaction can decrease that temperature by absorbing that energy. So absorbing means it is moving towards endothermic direction. And if you decrease the temperature, the reaction prefers exothermic direction. Any problem with this?
Because they will increase the temperature, right?
Yes, because exothermic means it gives out heat. It gives out heat. So gives out means it will increase the temperature. We talked about this in the chapter for energy. So this is
So
what you
if-
need to. This is what you
So-
need to learn. Yes, sorry.
Sorry, if you decrease the temperature,
Hmm.
then the reaction will want to increase it, right?
Yes, and the way to
So-
increase it, prefer the exothermic direction.
Okay, because yeah, exothermic. No, but exothermic gives out heat.
So that is how it will increase. Like if you are burning something, it gives out heat, so the temperature increases. That's how you cook your food.
Yeah, okay.
When you burn the gas, it is an combustion is an exothermic reaction, so it gives out heat, and that heat is absorbed by the food and it gets cooked up.
Okay.
Now our problem is, how do we know in a reaction? How do we know in a reaction? Let's say, for example, again the same reaction I'm using. How will you know which direction is exothermic or endothermic? Because we cannot memorize all of them. We know that when you increase the temperature, it favors endothermic. When you decrease the pressure, it favors exothermic. But how will you know which direction is exo or endo? Because I'm not talking about here forward or backward. Did everyone get this?
Yeah.
The examiner will give you this by two different ways. One way is they may write over here delta H is minus, let us say they will say 413 kilojoules per mole. Now this negative sign means exothermic. This is always for forward, always. So when they give you the value, that value is always for the forward. Is this in clear?
Yes.
So when they give you the enthalpy change,
For a
value is
reversible
always-
reaction, for a
Yeah.
reversible reaction, that value is always for the forward direction.
okay.
So from here, I know that the forward direction is exo, so the backward has to be endo. So this is one way. They can give you an idea of which direction is exo and which direction is endo. The other way is easier. On the arrow itself, they will write it as exo, so you automatically know it is endo. So these are the two ways. Either they will give you this or they will give you this. Clear?
Yes.
Okay. So now let's try to use this. So we have been given this reaction. Let us say I have been given this information already, that the forward is exo and the backward is, so the backward has to be endo. It will always be opposite. Now let's say I increase the temperature. What will happen? The first point, the equilibrium will be disturbed. The equilibrium is disturbed, that's the first thing. So what will the reaction do? The reaction prefers
The left.
endothermic.
No, not the left.
The
You don't say left.
endothermic direction.
Yes, very good. Reaction prefers a direction to oppose this. Oppose or oppose this. So oppose means prefers endothermic. So you have to say this endothermic. Now in this reaction, you would say the reaction shifts to left, or the equilibrium shifts to left. Is this thing clear? For this reaction. And if the equilibrium shifts to the left, Tasneem, what will happen?
Temperature is going to decrease.
No.
So, products decrease. Products
very
decrease.
Good. Very good. So the percentage yield or the yield of the products decreases. Now suppose instead of this reaction, I had taken this reaction. This is PCl3 plus Cl2. Now in this case, if I increase the temperature, what would happen? Yes, please.
Equilibrium is disturbed and the reaction prefers the exothermic direction.
No. It's still because you are, what are you doing? You are increasing the temperature. Increased temperature always prefers endothermic direction. In this, the first example, it prefers the backward. In the second example, it will prefer the forward. Did everyone understand this?
Yeah.
So you have to first of all say that the increased temperature favors endothermic direction. After that only you will look at the reaction given to you. Which direction is endo? Like in the first example of ammonia, the backward direction was endo, while in the second reaction, the forward direction is endo. Is this thing clear?
Yeah.
So in the second example, what would happen is the equilibrium will shift to the right side, so you will have more of the product. Any questions for this?
No.
Same way over here, if I decrease the temperature, I'm talking about the first reaction. This was an additional example. So if you decrease the temperature for ammonia reaction, again the equilibrium will be disturbed. The reaction prefers a direction to oppose it. Now what will happen? It will go to the exothermic direction. Now exothermic direction is forward. So the equilibrium shifts to the right. And if it shifts to the right, that means the percentage of the product will increase. Is this thing clear?
Okay. Yeah, teacher, you know the second example you gave of PCl5?
Yes.
So over there, the equilibrium is disturbed and it still prefers the endothermic.
Which condition? For increased temperature.
Increased temperature.
Yes. Correct.
Yes. Okay. So it prefers the endothermic, and the reaction shifts to the right, though, or the
yes.
left?
Right, because
right,
which direction is endo? So it's right over here. It is the right direction which is endo.
Yes.
So that's what I was saying. What you need to learn is when you increase temperature, reaction favors endothermic direction. Then look at the reaction. Look for the reaction. Which direction is endo? Because every reaction would be different.
Okay.
Clear? In some reactions, the endothermic would be the forward direction. In some reactions, the endothermic can be backward. So accordingly,
Yes.
you have to change your answer. But this statement is always true. Up to here, it is always true.
Okay.
It's only right or left that depends on the reaction. Any questions?
No.